The next presenter here is Krasimir Doino from ExxonMobil, Houston. So, the floor is yours.
Good morning, ladies and gentlemen. My name is Krasimir Doino. I'm from ExxonMobil Development Company. I'm a Risers advisor. In the development company, we do deal with the development of the new fields. So my focus is mostly going to be based on design, but I will also touch on operational activities as well. My background in flexibles is back from the 90s when I worked in Wellstream Panama City factory. I joined Exxon after the merger between Exxon and Mobil. And my management at the time said, no, here is a guy who must understand something about this complex technology. And ever since then, I have been supporting ExxonMobil projects and operations for issues regarding flexible pipes. I have been also chairing the flexible pipe standardization activities of API 17J, B, K, and L, and ISO counterparts. And when Trond asked me to give a presentation here, I decided that that might be a good position to talk about improving standards and technology towards achieving robust design and safe operation of flexibles. The outline of my presentation, I'm going to share 3 examples of safe practices used by ExxonMobil that were accepted by industry for incorporation in the upcoming 2014 editions of API 17J and B. Then I'm going to highlight some of the key 17J and B improvement areas from lessons learned by the industry over the last 15 years. And I'm going to conclude with outlining technology development priorities on which ExxonMobil is acting on its own in cooperation with manufacturers, consulting companies, and in a JIP settings. ExxonMobil has about 20 years of design and operation experience with flexibles. We have approximately 400 kilometers of installed risers, flow lines, and jumpers. On the dynamic side, we have offloading systems, dynamic risers to FPSOs, fluid transfer lines between tension leg platforms and FPSOs, and jumpers to static up to hybrid risers to FPSOs. We have some quasi-static service jumpers to top tension risers, and lots of flow lines and subsea jumpers for infield lines. The geographical spread is offshore UK, Norway, West of Africa, Canada, and the United States. The water depth ranges between 100 meters and 800 meters of water depth. My first example is with outer sheet damage and fire tunnels conditions. Back in 2009, SureFlex JP concluded that approximately 25% of all damages reported to JIP was suffering from damaged outer sheet, and about 35% were with fire tunnels conditions. We have similar numbers and causes in some of our West of Africa ExxonMobil fields. The damages due to installation, abrasion from the seabed, blocked ports, or accidentally direct mooring chains on top of flexibles. The first thing is that we realize that once the water gets inside the animals, we cannot get the water out of it, so we have to live with it. And there are not too many repair options. We can only clamp the outer sheet in order to prevent the oxygen inflow. The key failure mechanisms are gradual ones: corrosion fatigue, and accelerated aging of polymers. So this is not something that the flexible riser is going to fail immediately after fighting the animals, but it's going to take some time to develop eventually to tensile burst or fatigue failures. The key uncertainty is that everything that thing happens, our operational folks are asking the question, okay, what is my remaining life and when do I need to replace the riser? And which in turn is linked to wire corrosion fatigue and polymer aging capacity. The key technology gaps that are out there is very difficult to inspect and monitor reliably the animal's conditions, to check wire stresses, to determine how many wires we have broken, or to determine corrosion and aging status from animals' composition data. And there is a lack of industry consensus on selecting testing frequency for establishing corrosion S-N curves, and also design and test methodology for synergistic effects. For example, a combination of corrosion plus fatigue or aging plus fatigue. So the fundamental premise of ExxonMobil design and qualification testing standard is that inspection and monitoring should not be used to compensate for a lack of robust design, even if they are both available and reliable, which is not always the case. Back in 2005, we changed our standard to require design for fire tunnels conditions for the entire service life of risers, meaning assuming installation damage followed immediately by repair, and requiring the design S-N curves to ensure 97.5% probability of survival. At the time when we looked at what the manufacturers had to offer, they would have corrosion S&N curves built on a small test sample size, about, for example, 11 points. Means that if you use the regular formula of mean minus 2 standard deviation to establish a design S&N curve, you're actually ensuring about 90% probability of survival. And we wanted to go with what we understood, which was 97.5 as it comes from the steel riser world. The current 2009 edition of 17J and B, we have only a requirement for design for dry nose conditions, while fatigue life for fire dry nose conditions is provided for information only. The new upcoming 2014 editions, which are going to be released in the first quarter of the next year, they have design requirements for fire dry nose conditions. So the first point is considering fluids in the annulus predicted by condensation, assuming intact outer sheet. The second scenario is exactly the one that I mentioned, assuming installation, from day number 1 followed by repair, which is for deaerated seawater. The third one is accidental scenario for aerated seawater, for example, between 2 ROV inspections. And this is going to have impact on the material selection and performance in their design with associated degradation mechanism. I quoted here one of the new requirements that illustrate that point. The anti-buckling tape structural capacity shall be defined as the minimum strength during the pipe service life after accounting for aging and wear. So that is where we're heading. The second example is of an inner sheet damage for a smoothbore water injection riser. So what happened is that we accidentally lost an umbilical. And because of that, we had to frequently shut down a water injection riser with the sequence of closing a topside valve first, followed by the subsea valve. And in that process, there was a vacuum being drawn in the hang-off point of the riser. So every time when we drew vacuum, then the inner sheet collapsed simply because of the differential from the atmospheric pressure. And after repetitive collapsing of that plastic sheet around the hard steel edge of the end fitting, eventually, that sheet ruptured. So that's what you can see here. This is a picture taken from inside the end fitting. Once this one ruptured, then the pipe lost containment and resulted in bursting of the outer sheet, as you can see here. So in 2005, we changed our internal standards to require the use only of round bore pipes, simply because we cannot design a smooth bore pipe for a scenario like this. The current 2009 edition of 17J and B, there is no design requirement for collapse of a smooth bore pipe. However, there are recommendations for collapse calcs, erosion speeding, and factory acceptance tests. In the new 2014 editions, we added design requirements, which for collapse calcs per manufacturer's acceptance criterion, and consideration of a requirement actually for introducing anti-collapse sheets, and so corresponding end fitting sealing, FAT test, and annulus pressure testing. And the third example is about corrosion reservoir souring. We had a 55-degree structure installed back in the mid-90s. It was designed at the time for squid service. At the time, we failed to predict the reservoir souring. That happened fairly recently. As a result of that, the sweet wires fractured due to the presence of hydrogen sulfide, and the supported pressure sheet consequently cracked. So then we had to replace the entire field from sweet service flexibles to sour service flexibles. And before we did that, we retrieved our pipe to analyze exactly what was going on, and we look at the damaging mechanism. So what you see here is the 55-degree angles for the 2 tensile layers, and you see an unsupported area of the pressure sheet, and on the bottom picture is simply the pressure sheet kind of ruptured. We did a lot of FE analysis trying to understand, playing different scenarios, what was the most likely that took place resulting in this failure, and we understood that some of the wire stresses were not only beyond the stress utilizations for the layer, which was 85%, but they were going beyond the 90% of the yield. So that was the time when we reconsidered seriously how we need to requalify the sour service flexibles, and we change our sulfide stress cracking and hydrogen-induced cracking test to require testing to up to 100% of the actual yield strength. And then to impose the strains and the residual stresses on the wires, prior to doing testing, meaning those stresses were supposed to be representative of as manufactured wire. The current edition of 2009 of 17J&B, those tests currently are required for 90% of the actual yield. In the upcoming version 2014, we have these requirements to test two loads equal or exceeding the calculated maximum local stress on the wire from FE analysis, and that the test wire specimen should contain the strain and residual stress representative of wires as retrieved from the pipe. Next, I'm going to highlight some of the improvement areas in 17J&B. I must say that the upcoming 2014 edition includes lessons learned from about 15 years. So this includes pretty much all the flexible pipe JPs prior to the flexible pipe technology JP, which was tasked to improve the standards. And that JP, which PSA was part of, was run between 2005 and 2012 with 19 companies representing operators, regulators, all manufacturers, consulting companies. Following the completion of that JP, we withdrew about 800 comments over the last 2 years from the rest of the industry. So as a result of that, all areas of that standard, meaning manufacturing, testing, design, analysis, including integrity management, which I missed to mention here, have been improved significantly. What I'm giving you is just a snapshot of some of the definitions. We kind of try to align the pressure and temperature definitions with those of the existing steel, riser, and pipeline standards. We introduced this structure that you see here on the right, where in the upcoming version we are separating the incidental from the design. Currently they're combined, and we are introducing a pressure profile, which is whatever the operators envision how the pressure is going to change throughout the years. We introduced similar structure for the temperature as the one for the pressures, and this time make clarification clearly that the FET test can actually be based on a differential pressure as opposed to design pressure in certain cases, and introduce definition of an offshore leak test, structural integrity test on board of an installation vessel, or structural integrity test in situ, meaning for accidents that happen during installation you have to repair and then you can put the line back in action. The next is introducing the changes into design acceptance criteria. What you're going to see is that a new column, we have no survival conditions. Again, this is bringing the flexible pipe standards in line with the steel riser standards, which allow utilization up to 1.0 for the steel risers. Well, we're going to about 97%, and the reason being is that we're stepping on assuming nominal geometry considerations, as opposed to if we require 1.0, we would require the manufacturers to pile all the manufacturing tolerances in the worst possible way. Other changes that we are removing the water depth dependence from carcass collapse calculation. Now it's only one value. We're introducing design requirements for anti-collapse sheet, and the anti-backing tape is now a structural layer as well. And what we're relaxing is the stress utilization for the pressure armor for normal operating conditions. And the basis of that is a reliability study that we performed during the flexible pipe technology JP, which was pretty much based using first order reliability method and Monte Carlo simulation, about 1 million of them, for 3 pipes, design and material properties provided independently by the 3 flexible pipe manufacturers, NKT, which is nowadays NOV, Wellstream, and FlexiFrance. So what you see on the graph, on the horizontal axis is failure probability, and on the vertical axis is stress utilization normalized by the yield. And this green dot here represents the current design criteria of 55%, which is positioned at probability of occurrence 10 to the minus 4. And what you see with the solid lines, this is the result from the reliability study, and the upper lines represent the failure probability versus stress utilization for the hoop strength layer, while the lower lines represent the failure probability versus stress utilization for the tensile layers due to the end cap effect. So it's sufficient to say that there is plenty of margin existing in the way the manufacturers currently design those pipes. So that's kind of the basis on which we relax the criterion from 55% to make it equal to 67%, which is the same for the tensile layers. Another addition is recommendations on local stresses for individual wires. They are non-existent at this time in the current version of 17JNB. We included that in the upcoming version of 17B. So the first point is that we need to account for residual stresses in wires due to manufacturing and FAT, which is specifically very important when you account for fatigue life calculations, especially on the hook strength layer. We have a recommendation to keep the maximum local stress in a wire below the yield. And then I also already mentioned that the HIC and SSC test should be done at the maximum local stresses plus having the residual stresses introduced into the wire specimen. And that's for those rare cases where the stress exceeds the yield, then we're introducing a strain-based design to account for that, which is going to be followed by choosing some of the load cases for the full-scale fatigue test to include that type of loading. The next slide is about the new additions into the testing sections of 17JNB. We have introduced definitions for prototype, qualification, verification, and validation tests. We added property testing and quality control requirements for the end-tape buckling tapes. We have made clarifications to FET hydrostatic pressure test to clarify holding period and acceptance criteria, simply because there were numerous requests for interpretation of the current rules received over 10 years, so we had to address those. We have introduced a new structure for all of the FAT and prototype tests, specifically purpose, procedure, acceptance criteria. Provided guidance on scaling and similarity assessments for when choosing which pipes to need qualification testing. We introduced 5 test levels and acceptance criteria for different test objectives. For example, here, every single strength test can be tested either to failure of the pipe or the end fitting. The second level is to the ultimate tensile strength of the critical component. The third level is to the yield strength of the same component. The fourth level is up to the utilization factor per 17J table 6. And the last one is to the maximum load. And the logic is that if you test at the lower level, you're going to automatically cover the objectives of the higher levels. Similarly, for fatigue testing, we have test failure, testing to a target testing curve, which is typically defined as mean plus 3 standard deviations, testing to a damage ratio of 1.0 for the critical fatigue component, testing to the design acceptance criteria, which includes the safety factor of 10, or to the maximum damage accumulated in a fatigue lifetime. Next is an example of different objectives offered for each test. Specifically, this is for the fatigue test. You can either choose to qualify a flexible pipe for dynamic service, verify manufacturer stated fatigue performance, or validate service life design methodology and tools. And you can use either destructive or non-destructive tests to achieve every one of these objectives. So, for example, for the non-destructive tests, validation of design methodology and tools can be done if you instrument the test piece properly and take some measurements. The bottom table presents examples of different design acceptance criteria for, let's say, for tensile failure of flexibles, and what we have a failure in the pipe body versus failure in the end fitting, and different scenarios when the predictions of the failure tension in the pipe, for example, are above the ones that we measure, but the predictions of the failure tension of the end fitting are below what we measure, then the acceptance criteria is accept the pipe body, change the end fitting design, or derate the tension capacity, and rethink your end fitting design methodology. Next is an example of our corrosion fatigue efforts. The current industry practice is to derive corrosion S-ing curves based on virgin wires. However, the concern is that if we had this scenario of flooding the outer sheath, kind of damaging the outer sheath and flooding the riser from installation, throughout the first year, those steel wires are going to create some pits. So this means that the remaining of the lifetime, which is 90 plus years, instead of doing a fatigue of a virgin wire, we're going to have fatigue of a corroded wire. And another practice is that testing corrosion S-ing curves typically is done at 0.5 hertz or higher frequencies. And really now the concern is that faster frequencies tend to negate the potential deleterious effects of the environment, and then loading frequency should be slow enough to allow these processes to take place. So what you see here is the test samples, which is subjected to tensile tension, and we're introducing an EDM notch where we are trying to screen the testing frequency versus the crack growth rate, which is shown schematically here on this picture. So essentially, when we test in air, we can test at very high frequencies. However, when we test in environment, when we decrease the frequency, we're going to see that the crack growth rate is increasing, and it will do so until a point beyond which further decrease of the test frequency is not going to yield any change of the crack growth rate. So that is the methodology by which you are determining the maximum testing frequency for the given environment that catches all the chemistry, corrosion chemistry properly. On this figure, what you see is really low test data following this approach. On the vertical axis, we have a crack growth rate. On the horizontal axis, we have the crack size, which is normalized by the width of the wire. So we start with testing at 10 Hertz in air, then 10 Hertz in a sour environment, followed by 3 Hertz, 1 Hertz, up to 0.01 Hertz. And then we're increasing the frequency backwards, simply to clearly see this effect. What is shown here on the right-hand side of the picture, we spent some time to learn how to acceleratedly pre-corrode the wires and put some pits in it. Then this picture really represents a scan with white light interferometry that characterizes the pits. So we learned how to characterize them statistically. Now we're in the process of doing fatigue testing to correlate the different pits with the fatigue resistance of the wires. And my final page is, these are the technology development priorities that, as I said, ExxonMobil is working on its own with cooperation with manufacturers, consulting companies, and JP settings. The first emphasis is improvement of, additional technologies and improving the analysis methodologies for riser response, specifically for fatigue, bend compression, and lateral buckling is a key in order to push this technology for deeper waters. Developing testing methodologies that capture chain reaction of synergistic effects to establish component capacity, as I mentioned, for wire corrosion and fatigue, high-strength tape wear aging and fatigue, polymers aging to different exposures, which are not standardized yet. That's what one mentioned, that Fort Subsea is going to be managing this JP for 17TR2, which is going to stay with the same number. It's just going to be renamed to aging of polyamides as opposed to aging of PA12. We have joined that and recommend everybody else to do so if you haven't done so yet. And finally, to develop methodologies that correlate annual sampling history to wire corrosion and polymer aging. On the new design, the importance is expansion of the application envelope, and specifically to increase the water depth for existing diameter times pressure, which essentially means weight reductions. What we have done in the upcoming version of 17B, we introduced as Annex H that actually introduces a framework for the introduction of composite materials and components and layers into the unboarded flexible pipes. Then the other area is material and layer design improvements for corrosive environments, specifically for souring reservoirs, which is a fairly kind of recent phenomenon from the 2000s. And for the strange environments like the Black Sea, where we have hydrogen sulfide and no oxygen whatsoever beneath a water depth of about 200 meters. And finally, these are remnant life assessments. What we need to improve is the inspection technologies on layer and component levels. And of course, everything that I mentioned on the predictive technologies, if it's developed, it's going to help remnant life assessments. This concludes my presentation, so I'm ready to take some questions.
Thank you, Krasi. Any questions?
Well,
I see Klaus has one there.
Hi, Klaus Christensen, Statoil. Thank you for a good presentation, Krasimir. Very interesting. I have one question regarding the Table 8 update and the utilization of 0.85 for the carcass. Do you feel that the methodologies for predicting bended collapse is sufficiently strong to allow for that?
Could you please repeat the question? I didn't hear it from this noise.
Regarding the increased allowable utilization of 0.85 for the carcass collapse, do you feel that the methodologies for bended collapse are strong enough to allow for that?
Well, it's the removal of the water dependence. It was only for shallow water, and the thought at the time of why we had more stricter requirements for shallow water was simply because of the uncertainties of the tidal variation. So that was simply associated with lack of understanding of meta-ocean criteria. But these days, at least in our camp, we provide a very good definition of what the water levels are and how they might change, including the surge variation and the tidal variations. So that uncertainty is kind of removed already in most of the places, and that was the reason why we had structured collapse criteria at the time. Removing that uncertainty does not require this distinction anymore. So the 85% is still kind of a good safety margin in my opinion. It's a different story that I understand that there is a plenty of carcass collapse issues, but I'm not sure that they're related to dust ring utilization. They have most likely different sources.
Okay, I agree. Thank you.
Any more questions?
Charles White, engineering manager for Kanawha, BG. This is probably a question better for the end of the day, but I'm curious about your opinion on it. And that is, are these predictive techniques at a point to where we can actually act on them, or are we just getting a little more insight from them today?
Well, the three examples that I provide is something that we certainly understand and which acted on it, and we acted on it of changing our standards and eventually convincing the industry to do so. However, we're not at the point where we can push that understanding further down the road. So for now, it's just our own internal understanding and helping our own operational units to deal with accidents that, whether we like it or not, tend to happen. But we're not ready for a prime time yet. But we're going to publish a paper in the OME conference next year in San Francisco, detailing regarding the frequency scanning for corrosive environments, pre-pitting of the wires, and kind of linking that behavior, the pits, with the fatigue resistance. How you fine-tune your fatigue resistance, for a certain environment, so that you can help your own operational folks. So we're making that available this coming OME conference 2014 for the first time.
Thank you.
Okay, one more question or two.
Thank you, Krassi. That was a good presentation. I'm Charlie Smith from Shell in Aberdeen. I think we've spoken a couple of times over the phone. Good to see you face to face. Related to Klaus's question on utilization factor of the carcass, you mentioned in part of the presentation that the new update will allow for local stresses. Given that the carcass is plastically deformed during manufacture, there will be high residual stresses. Are you still satisfied that the 0.85 utilization factor gives us enough margin against collapse?
Well, the 85% of the carcass collapse is on a layer level. The local stress is, what I meant was mostly focused on the hoop strength and the tensor wires, because that's where they matter a lot. For the carcass, whether we should go to lower utilization factor, whether that should help, we first need to understand what is the reasoning of what is the fundamental reason why this carcass collapses. I'm not really convinced that we're questioning this utilization factors of 85%. I think the reason might be somewhere else, and I hope to hear a little bit more about that from Klaus's presentation. But but that's kind of in essence what we're doing is what we look at the flexible pipe technology. JP had 19 different companies coming to the table, sharing their lessons. We had a discussion like that, but we only acted to change something when we understood where is it coming from and why we are doing it. So it's premature to say only because we have experienced some carcass failures here in the Norwegian sector of the North Sea, to jump and change the utilization factor before we understand, why is it happening.
Thank you.
Last question back there.
Hey, Paul Gundersen, Kongsberg. Has there been any discussion whether internal flows such as slugging should be dealt more in the API new edition?
Yes, we do have language about accounting for slugging. However, this is still a kind of field that we are still trying to understand. There have been some failures due to slugging, but not to flexible pipes, not to my understanding. So literally, before you see failures in the field, you cannot standardize specifically for that. So we do have language to account this from fatigue perspective. This is one of the fatigue sources. So that language is in there in the 2014 editions of the standards. However, to change, for example, our design practices only based on that thing, it is only one component for potential loading of the resin. There are so many different ones. So unless it's really important and it's fundamentally changing, the way we design, our flexibles, for now, what we have a language in the upcoming version is quite sufficient, to cover that subject. But yeah, as the industry, we are working on that, trying to understand more. There is a SWARP JP, which is chasing exactly, the effect of slugging on jumpers, steel risers, and flexible risers as well, that we are part of. So we're still trying to understand it.